Okay, can you see my screen?
Yep.
Okay. Welcome everyone to this online edition of the Graph Theory, Maze Generation, and Pathfinding event. We are also collaborating or joining this event with our November GBM. This is a 2-in-1 event. Because this is a solely online event due to the tropical storm Nicole, we will not be recording attendance for this event, but we're glad you're watching this on our YouTube channel. For those new around here, our Discord is listed right here on the screen. If you want to join our Discord is our primary form of communications for all things GDSC, Google Developer Student Club at UCF. So please join our Discord if you want to get all the latest news and updates from the GDSC. The tiny URL is tinyurl.com/dscucf-discord. And with that, we're going to jump into today's event. So this is a meeting schedule for today. We're going to start off with our November GBM meeting, where we'll discuss what is a GDSC, how you can get involved in the GDSC, and our upcoming events for November. Then we're going to shift gears into our graph theory event, where we'll talk about what are graphs, how to search a graph, and we'll also look into the A-star and Dijkstra algorithm. We'll have a cool workshop at the very end in order to demonstrate our understanding through the workshops or through the event. So first, let's start off regarding what is a GDSC. GDSC is short for Google Developer Student Club, and it is a sub-organization under a wider organization called Google Developers. And the point of Google Developers is to solely export a bunch of technology and resources that Google develops and establishes. As a result, there are other Google Developer-sponsored organizations such as Google Developer Experts, Women Tech Makers, and Google Developer Groups. The Google Developer Student Club is dedicated to registered student organizations all across the world, helping teach and learn about Google resources and technologies. Our mission as a Google Developer Student Club is to help students bridge the gap between theory and practice. But what does this mean? In class, we learn about a lot of theory regarding computer science and IT, but we never really put that into practice. As a result, here at the GDSC, we help students bridge that gap and actually practically apply what they learn in class. By joining the Google Developer Student Club here at UCF, you'll have hands-on experience with real industry tools with real practical applications. On my screen here is a wide slew of Google technologies that here at the GDSC, we have a lot of resources to give to y'all and teach you about and host workshops about. However, the GDSC isn't constricted to just Google technologies. We can host workshops on anything. It is a student-run community at the end of the day. So whatever you guys want to say or want to learn about, here at the GDSC, we'll create a workshop for. Thus, we are a peer-to-peer learning environment. We are stronger as a team. By joining the Google Developer Student Club, we hope that you can meet new people, make team, build projects, and most importantly, play with technology. Because we're a student-run organization, we routinely grab feedback from our Discord and other forums in order to work better and create a better club for all of y'all. So if any of that sounded enticing or you're interested at the GDSC, we want you to please join. We're open to all majors. It's very easy to join the UCF Google Developer Student Club. On the link here is a tiny URL that links you to a slide deck. And on that slide deck, you'll have access to all our socials, our calendars, how to sign up for our mailing list, and how to sign up for our Bevy, which is our Google created RSVP sites, and much more. So please join this tiny URL or use this tiny URL, scan this QR code to access this tiny URL on the screen here. It's very important if you want to join the GDSC formally and get all the latest updates. And we're also going to put all these links in the description of this YouTube video. So if you don't have your phone on you right now, or you can't scan this QR code or don't want to type this link, it will be in the description. So with that, we're going to talk about our upcoming events in November. So please mark your calendars for these announcements. Our first upcoming event is called Leak Code and Problem Solving Strategies. It is on Monday, November 14th at the Business Administration 1 building, 214 from 6 to 7 p.m. In this event, you're going to learn strategies for tackling new programming problems and practice a slew of leak code related problems that you often would see in technical interviews. Students of all experience levels are welcome. We'll go from one end to the other during this event. So I highly encourage you, no matter how many leak code problems you've done, either 0, 100, or 500, to please come to this event, as we'll make sure it's accessible and you'll learn and gain something out of it. The next event will be just 2 days after. It is our SQL Murder Mystery event. It is on Wednesday, November 16th from 5 to 7 p.m. And this is going to be a little bit more of a fun event. We're going to have a murder mystery themed workshop where we'll be incorporating a lot of SQL concepts and commands that we'll teach you during the workshop as a fun game, so experienced SQL users can solve an intriguing crime. And if you are interested in this event, please mark your calendars. We'll also be posting about it on our Discord, so please check out there. But if you're interested in any other topics, let's say you're not really interested in these technologies, we have a topic interest form in the bottom right, where you can actually contribute and tell us what workshops that you want to see in the future. So if there's anything here that you want us to post a workshop on, please fill out this form here on the bottom right by scanning that QR code. We go through the topic interest form routinely and host and base our workshops off of it. So your feedback is greatly appreciated. With that, we're going to jump right into our graph theory event. So usually there'll be a little break here, but if you want to take a little break right now on the YouTube side, you can pause it here. And until then, we're going to get started with our graph theory event. So the first thing we're going to answer, of course, is what are graphs? And a graph, all it simply is a mathematical concept to notate a set of vertices and edges. And sometimes throughout this workshop, you're going to see me and Carlos here refer to these vertices as nodes as opposed to vertices, but you can interchange the terms. They both mean the same thing. And if you see here in the middle of the screen here, this is the mathematical way to write this. G is equal to a set of vertices and edges. And sometimes they can be represented like graphically like this. So as opposed to using set notation, which was what we saw on the previous slide, you can actually draw these graphs. So for example, on the left side right here, you can see that this is a triangle with 3 vertices, 0, 1, and 2. And these vertices are connected by these edges here. So I can see that 0 has an edge with 1, has an edge with 2, and the same thing for all of these. This graph in particular, what you'll see is that every vertex can access every other vertex. For example, there's 3 vertices here. At vertex 0, I can access 2 and 1. At vertex 1, I can access 2 and 0. My bad. Yeah, 2 and 0. And at vertex 2, I can access 1 and 0. This is what we call a complete graph. It is where you can access every other vertices from every vertex. And we can represent this as K. So K3 means it is a complete graph with 3 nodes. So this is a K3 graph, complete graph. Additionally, this is also a cycle, meaning that I can go all the way around this graph and I'll never end. There's no dead end. It's quite literally a cycle. And thus we can represent that as C3, which means a cycle with 3 nodes. Now, these are very universal. So if I say K3, I can place these nodes elsewhere, but the same idea will persist. There's 3 nodes that I can access every node from every node. So as a result, here we can see this is another graph, and this is also a complete graph, but this one with 4 nodes. So as you see, it looks a lot more complex than a triangle, but it is the same exact concept. I can access every node from every node. The last concept here is actually very interesting. This is almost a complete graph. As you see here, from 1, I can access 0, 2, and 3. From 0, I can access 1, 2, and 3. But from 3, I can only access 1 and 0. I can't access 2. And 2, I can only access 1 and 0, and I can't access 3. In other words, if there is a edge here, this will be theoretically a fully complete graph, just like this one with 4 nodes, but there isn't. As a result, because graphs are mathematical concepts that can be notated using set theory, we can actually use the same exact notation to indicate that this is a complete graph that is missing one edge that makes it a complete graph. So this is just a cool little thing for those who have maybe learned graph theory before, but not known that you can actually represent your graphs like this. Very cool. So now we're going to talk about how to search a graph. And there's 2 primary ways to search a graph. And here's just a short description of both of them, just to maybe refresh your memory if you've worked with graph theory before, or if you've never seen these before, I would come to this just to get a bare understanding of it. So the first way is called depth first search. And the idea is very simple. You start at any node or vertex, and you keep walking until you hit a dead end, and then you backtrack. It's very simple. We'll look into more detail of how this is practically implemented. And then the next way is called breadth first search. This one may seem a little bit harder to explain, but they're both just as easy, I would say personally. Everyone has their preferences. Some problems would require you to implement it different ways. But the idea is you start at any node, let's call it U, and you keep track of its neighbors, basically all the vertices that you share an edge with, and see if they've been visited in V, which is what we're using to keep track of visited nodes. If not, then we're going to mark it as visited and move on. So that's just a very, very dumbed down explanation of breadth first search. But once again, we're going to go into a little more detail so we can see exactly how both of these searching algorithms work. First, we're going to start with depth first search. So I have this graph right here on the left-hand side. You see we have 6 nodes here, notated 0 through 5. And I'm going to choose any node to start off with. That's what depth first search, or that's what I'm going to do in depth first search. So I'm going to decide to start on node 0. So I've notated here in green that I'm starting at node 0. The first step that I need to do is I need to initialize a visitor array. And this will just represent all the nodes that I visited. So I'm going to create a visitor array here. This is just 6 values here to represent the 6 nodes, and I'll initialize them all to false to indicate that I haven't visited any node. The first thing I'm going to do is I'm going to mark node 0 as visited. Because I'm starting at 0, I'm just going to say that I visited that because I quite literally did. And then what I'm going to do is I'm going to go to any neighbor. So this is essentially what we talked about before, where you just walk somewhere, anywhere, until you hit a dead end and then backtrack. So here I have 3 options on where I can walk or go to from node 0. I can go to 2, I can go to 1, I can go to 3, and I've represented this in red. So let's just choose any of them. So let's choose 1. So I've decided to walk this path towards node 1. So now we're at node 1. Now what we're going to do is mark node 1 as visited. So in my array up here, I'm going to mark node 1, index 1 as visited. So I'm going to make that true. And then I'm going to go to any unvisited neighbor. I wouldn't want to go back to someone that's already visited because that's just redundant. So instead, I'm going to now actually utilize this visitor array to see what nodes I should visit next. So from 1, I can walk to either 2, 0, or 3. Now node 0, I can see in my visitor array has already been visited. So I can wipe that off the possibility. There's no way I'm visiting node 0. Now I can either visit node 2 or node 3. So I'm going to choose node 3. So now we're at node 3, and it kind of goes the same here. We're going to mark node 3 as visited. So at index 3 here, I'm going to put as true. And then I'm going to go to any unvisited neighbor of 3. So in red here is all my possible paths. And as you see here, I can either go to node 1 or node 0. But node 1 and node 0 have both already been visited. You can see that they're green already to indicate that I visited them, or I can check this visitor array like they've been visited. So I'm kind of stuck here. And this is what I mean when I said earlier that I have to backtrack. When I can't walk anymore, in other words, I've hit a dead end, I'm going to backtrack. So I'm actually now going to go backwards. So no unvisited neighbor, I'm going to backtrack. So now we're back at node 1. So remember, we went from 0 to 1 to 3. There was no neighbor. So now we're back at 1. So from here at node 1, I'm going to go to any unvisited neighbor of node 1. So right now I can see from node 1, I have the options of node 0, 3, and 2. And node 0 and 3 are both visited. I can see in the array, 0 and 3 are both visited. I can see in green here that they're visited. So my only option is to go to node 2. So we're going to go to node 2. So now we're at node 2. And we're going to repeat the steps. We're going to mark node 2 as visited in this array from false to true. And then I'm going to go to any unvisited neighbor of 2. From 2, I can see that 1 and 0 has been visited. So my only option is go to node 5. So I'm going to go to node 5. Now we're at node 5, and we're just going to repeat. Mark node 5 is visited in our array. So I think this is the 5th index, so it's false. Now it's going to be true. And then we're going to go to any unvisited neighbor of 5, 2, and 4. 2 has already been visited, so my only option here is to go to node 4. So I'm going to go to node 4, and now we're at node 4. At this point, the last thing I'm going to do is I'm going to mark node 4 as visited. So from false here to true. And one thing I realized immediately is we visited all our nodes. My entire visited array is marked as true, and it's kind of the end. We've searched the entire graph. So we can go to any unvisited neighbor, but I see that there is no unvisited neighbor. There's no need to backtrack either because we visited everything. So we're kind of done. And in black here, I've indicated the exact search, the traversal of all the nodes that we've went on. So we started at 1, or my bad, we started at 0, we went to 1, 3, 2, 5, and 4. And we don't count that time we backtrack because we've already visited before. So theoretically, if someone was to give you an interview problem or something along the lines of start at node 0 and draw a valid or write a valid DFS traversal, this would be a valid DFS traversal, 0, 1, 3, 2, 5, 4. And there's many possible DFS traversals. This is just one of them. And it's a pretty good one to kind of show off that backtracking is sometimes necessary. But with that, it's very simple. So before we actually move on to breadth first search, I'm actually going to pass the mic on to Carlos here, who's going to talk a little bit more about practically applying this depth first search for maze generation. Very cool concept.
Hello, everyone. I'm Carlos, and like Ryan said, I'm gonna go ahead and share my screen. Ryan, you have to activate it for me. Meanwhile, so we're gonna take this DFS searching that we just did, and we're gonna actually apply it to a little maze generation. See, I can share my screen now. Okay. So, Ryan, you can see my screen? I think so. Okay, so we're gonna have this link over in the description of this video, so feel free to go to the link and check it out. And this is how we're gonna do our workshop today. We're gonna go to this replit that's been created, and we're gonna create a fork of it in your own account. So I'll just start doing that. Let's say cool maze thingy. Let's fork this replit. And now we have it running in your own replit, environment. Now, I do have some trouble often with this web view, so I suggest you just open it in a new tab. And now you have the actual website where all this is running loaded up. So as you can see, we have about 5 buttons, and we have one that generates maze. Right now, this isn't generating anything. It's just kind of filling everything with a grid and the start and end button, or cells, I mean. And there's really nothing that's happening. This is the button that we're going to implement right now. We can also clear the board, and we're also going to implement by the end of this the pathfinding algorithms. So let's go ahead and start doing that. Let's go over to the the replit environment where we have all of this code. And for this first section, we're going to create the maze using something called randomized DFS. It's very, very similar to what we just went over. The way that this is all working, by the way, we have a controller file. This just has n as in the columns and rows of the maze, and then the size dictates how many pixels it takes up on the screen. And then we have the generation file, which exports this randomized DFS function. By export, I mean that we have a maze.javascript file in this utils folder, and it's taking this function that we're going to create, and it will take care of running it. So all we need to worry about, you are free to check the maze.js in your own time out. It has a lot of repetitive work of drawing everything, but all we need to worry about is going to the generation file and implementing this randomized DFS. So let's begin. I left a comment here that explains that this function will be recursively called until it returns true. What this means is this function will keep getting called every single time until we return true. So we can think of this as returning a stop value, like do you want to stop or no? So that's how we're gonna go ahead and implement it. That's usually how DFS is implemented. Also, it's either with a stack or recursion. We're actually going to do a little bit of both. So we're receiving the maze. This maze is basically a two-dimensional array. It's a grid that contains all of the cells, all of these cells that we see here. And then we're also receiving current. Current stands for the current cell that we are on at the time that this is called. So the first thing that we want to do is with this randomized DFS is we want to do a DFS on the maze, but on a random child. So back in the slides, we would choose a child almost by random. We're going to do that here too. So let's start by declaring a next variable. And we have a couple of nice libraries already implemented for us. So we're going to take current and we're going to say, give me a random unvisited neighbor. And this will already give us a random unvisited neighbor. So this is the way that we are randomizing our DFS. This function will return null if there are no unvisited neighbors. So we want to make sure that this value exists before we start doing anything with it. So the first thing that we want to do is this cell that we receive, we want to mark it as visited. We want to say this cell has been visited. It has a visited value within itself. And this is the way that we're going to mark visited instead of using an array. This will just simplify things a little more. So then in order to help us with backtracking, we're actually going to go into the maze. We're going to go into a stack field that it has. A stack is basically, you can think of it as a stack of books. You put books on top of it. And when you want to take a book out, you take from the very top. So you take the last item that was pushed into it. This is going to help us throughout the whole backtracking of this algorithm. So what we want to do is we want to push into the stack the current cell. So the one that we are currently at, not the next one just yet, but simply the one that we are at. We're saying, push this into the stack. We're going to analyze a random child from it. So we're just going to do another helper function here, the highlight function. This is also implemented using the maze JavaScript file, and it basically just highlights this current cell on our screen so we can visually see what's going on as we run this. Now that we have a random unvisited neighbor, what we want to do is we want to remove the wall between this current cell and this neighboring cell. So what we're doing is we're going to every cell in the maze and we're saying pick a random neighbor and remove the wall that you have with it. And this actually serves as a really cool way to generate a maze in unpredictable ways. So now what we do is we set this current cell to be the next one. So now you may be asking yourself, well, when is the backtracking coming into here? So we just received a random neighbor. We pushed current into the stack. We removed the wall, and now current is next. How are we going to make sure we backtrack our way back through this maze? Well, what we need to do is we can check that as long as the stack has items in it, as long as the stack is not empty, we can start copying this stack. What this means is we're going to take out the last item that we put into the stack. This is what's going to allow us to backtrack throughout this maze generation algorithm. Then we'll highlight it. And then finally, we need to return true or false. Well, how do we know when we are done? Well, we know when we are done when the maze stack is equal to 0. When it's equal to 0, we know that we can stop. We've backtracked throughout all of the cells and we've created a maze. Now I will make this into an array because I'm actually going to return 2 different values. I'm going to return the stop condition, and I'm also going to return the current cell. So that's all that we need for this function. It's a relatively small function. The logic is not a lot, but it might take some thought to wrap around it if you've never used recursion or a stack before. So now that this is implemented, let's go over to the site where we have this loaded. Make sure to reload the site so that it loads the changes that we just made. And let's see what happens when we click Generate Maze. As you can see, we have this tiny purple cell that's running around. And if you notice, for every single wall, or apologies, for every single cell, there is at least one wall that has been removed from it for every single cell in this entire maze. And that's basically what we did. We made sure that we touched every single cell in a randomized way, and we just removed the wall in between them. So feel free to generate as many mazes as you like, and let's jump back into the slides.
Thank you so much, Carlos, for showing that cool implementation, practical implementation of DFS. We're going to jump right back into where we left off. Can you see my screen, everyone?
Yes.
Great. So that was a representation of depth first search. Now let's talk a little bit about the other searching mechanism, which is breadth first search. So breadth first search, we're going to use the same exact graph as before, and we're going to start at the same exact node. So here we're going to start at node 0. I've represented it in green. And this time we're going to initialize a queue and an array of visited nodes. So I'm going to represent this queue as just as empty box for now. And for those who are unfamiliar with a queue, it is basically something where I can take the very head of it, I can dequeue it at the very head, and I can add stuff to the very end. It functions quite literally like how a queue does in real life. Whoever's at the front of the queue gets out first, and when you're entering the queue, you enter through the back. So very simple concept. From here, what I'm going to do now is I'm going to add our node 0, because we're starting on node 0, to visited, just like we did in DFS. So I'm going to mark it as true here in the visited. Very nice. And now I'm going to add all unvisited neighbors of 0 to the queue and to the visited array. So before we were only adding, or we were choosing the unvisited neighbors and then doing the DFS steps all over again. But now we're going to mark them as visited right when we see them, not even when we go to them. Right when we see them, we will add them to the visited array and the queue. So here, for example, I've marked in red. From node 0, I can walk to or I can see nodes 2, 1, and 3. So as a result, what I'm going to do now is I'm going to add 2, 1, and 3 to my queue, and I'm going to indicate in my visited array that I visited nodes 2, 1, and 3. And this queue is very important because it dictates what node we're going to go to next. So let me just show this off right here. So the next step is we're going to move to node 2. And we go to node 2, like I mentioned earlier, because it's at the front of the queue. So I'm going to dequeue that very front of the queue. And once I decide to move node 2 or move to node 2, I'm going to pop it in the queue because I'm working with it right now. It is no longer in line. Now that I've popped it, I'm going to do the same thing. I'm going to add all unvisited neighbors of 2 now to the queue and mark them as visited. So from 2, I can see that I can walk to or I can see nodes 1, 0, and 5. Node 1, if I look at my visited array, has been visited before. So I'm not going to do anything with that. Node 0 has also already been visited. So I don't do anything with that. Node 5, however, has not been visited. So I'm only going to add node 5 to the queue and mark it as visited in my visited array. So I've added it to the queue and I've marked it as visited. Very cool. And now we're just going to do the same thing. We're going to pop the front of the queue. So now 1 is up next. Pop it. And from here, I'm going to add all the unvisited neighbors of 1 to the queue and visited. So 1's neighbors are 2, which has been visited, 0, which has been visited, 4, which has not been visited, and 3, which has been visited. So as a result, I'm only going to be adding 4 to the queue and the visited array. So now I've added it to the queue and the visited array. Very nice. And theoretically, we visited all the nodes here, but we don't have a full traversal. Thus far, I've only went from nodes 0, 2, and 1. I haven't visited every other node. And that's because in BFS, I don't finish BFS until my queue is empty. It's not when my visited array is fully, when we visit every array in the visited array. It's rather when the queue is fully unloaded, because that indicates that everyone who was up next to be visited has been actually visited. So as a result, we're going to keep moving on here. I'm going to move on to node 3 and do the same thing. I'm going to pop node 3. So now it's just 5 and 4. And I'm going to add all unvisited neighbors of 3 to the queue and visit. Like I mentioned earlier, we've already visited everything. So at this point, like this step is kind of redundant from our perspective. But when we implement it in code, like it'll be done. This step will be repeated. But like I said earlier, everything has been visited. So 1 and 0, I know have been visited. I'm not adding anything to the queue. I'm just going to visit the rest. So we're going to move on to node 5, do the same thing, pop it. It's been popped. Now I'm going to add all the unvisited neighbors of 5. All of these have been visited. So I move on. And then I'm going to move on to node 4, do the same thing, pop it. Now my queue is empty. Very nice. And I'm going to add all the unvisited neighbors of 4 to the queue and visited. Everything has been visited, and that's it. I have completely emptied out the queue. My visited array indicates that I visited everything, and I have traversed through the entire graph. So once again, if someone was to ask you in an interview or in an academic setting, a proper BFS traversal of this graph, this would be a proper BFS traversal. 0, 2, 1, 3, 5, and 4. It's a traversal. And I'm sure it has a lot of practical applications too, which we'll kind of lead on to a little bit later on, where Carlos will now take the stand and talk a little bit more about. So I'm going to stop sharing here and hand the mic off to Carlos.
Hello, everyone. I am back again. I will share my screen one more time. And we're going to talk a little bit about Dijkstra's algorithm. So if we look over to what we created in the previous section, we generated a maze, but now we need to be able to path find through that maze. And the first algorithm we're going to use is Dijkstra's. So when we have a starting cell and an ending cell, we need to find a path that can get us there. As you can see, I'm not very good with this myself, so I'll code it up and see how we can do that. Before we code it up, let's talk about the steps that we need to take. So Dijkstra's algorithm, it's a shortest pathfinding algorithm. So it guarantees that we get the shortest path. So let's try to visualize it and see what's going on. Over here, we have a bunch of vertices connected with edges in more of the manner that we are working with right now, which is a maze. So it's just a big grid of connected edges and connected vertices, or cells more specifically. We can imagine that this block over here are walls. There's no connection that can be made with them because they are a wall. So let's start going through Dijkstra's. We're going to, the first step for Dijkstra is we're going to go to every vertex in the graph and we're going to set its cost to infinity. In our case, we already have that done. And you can imagine that S, which I'm using it to represent the starting node, and E, which I'm using it for the ending node, they also have a cost of infinity. I'm just not showing it right now, just for the purposes of being able to see the starting and ending point. So Dijkstra's goal is to find the shortest path from the starting node given to every other node in the entire graph. So let's see what the next step is. We want to set the cost of our starting node, so this one over here, to 0. So let's go ahead and do that. The logic behind that is that if we are sitting on our starting node, it costs us 0 energy, let's say, to get there because we are already there. So that's our starting point for Dijkstra's. The next line in the pseudocode is it says that we want to add S, as in the vertex that holds our starting position, to a priority queue. So Ryan already covered what a queue is, but a priority queue adds a little twist for queue. It basically says that, say that I have 0 here, say I have 5 right next to it, and then 2 right next to it. As soon as I pop the 0 from the queue, if I want to pop another value, in a regular queue, it would be the 5 since it was right next to it. But in a priority queue, we actually prioritize the lowest value first. So we would actually pop the 2. This is very similar to a min heap if you're familiar with heaps. It's basically the same thing. And yeah, let's see what our next step holds for us. So when we put something in the queue, I'm just going to mark it with a yellow border, and that's going to mean that it's in the queue. So our next step is saying that we're going to run a certain block of code as long as the queue is not empty. Well, it's not empty, so let's go ahead and do that. We're going to create a new variable called current, and we're going to assign it the value of what we pop from the priority queue. So we would pop the 0, and current is now 0. It would be this node right here. Let's see what we do with that. So every time we pop from a queue, from our priority queue, I'm going to mark the node as visited. The logic behind that is that if I just pop the node that has the lowest value, I know that this is the shortest path to get there. Right now, this is completely true because 0 is the shortest path to itself. Let's see what the next step is. We're going to look at each neighbor of current, so of the starting node right now, that is not visited. So in our case, this starting node has 2 connections. We can look at this vertex right here or this one over here. Let's just go for this one just for the sake of it right now. The next step in the process is to create an alternate, a variable called alt, which for our purposes will stand for alternate route or new path, just an alternate way to get to that node that we haven't seen before. We're going to assign it the cost of the current node, so 0 right now, and we're going to add 1. We're doing this because we're saying from this node to this node, it's only going to take us 1 energy, 1 cost. So this alt is equal to 1. So if 1 is less than the neighbor's cost, which is currently infinity, for our purposes, 1 is way lower than infinity. So that this is true, we're going to assign to this neighbor's cost this new path that we found, which is going to be 1. So we're going to go ahead and do that. And then we're going to add the neighbor into the priority queue. Okay, so let's add into the priority queue and circle it yellow. Just as a reminder, yellow means it's in the queue. Let's keep doing that for the next neighbor. So this neighbor right to its right. If you realize, well, we're actually going to do the exact same thing. I mean, it takes 1 step to get here. Let's do that and add it to the queue. Let's go ahead and, so right now we completed a whole iteration of this while loop, and the queue is still not empty. So let's continue and see what happens. We just popped this one right here. So we're at this step at the current. We're going to go into every neighbor of this one, and let's start with this one up here. Well, when we pop, we mark it as visited. We're going to create an alternate route cost. So we take this one, and then we add 1. So the cost to get here would be 2. Is 2 bigger than infinity? Yep, then assign it the cost and add it to the queue. So let's go ahead and do that. We're going to assign it that, and we're going to add it to the queue. We're going to keep doing this at every step of the way with every neighbor. So now we're going to do that with this neighbor, and then we actually completed this one. There's no other neighbors to visit. So we're going to go ahead and pop this node now, and let's just rearrange that a bit. And we're going to go over to this node. We're basically going to repeat this process over and over, and let's just see what happens. So at this point, I think you've got a pretty good idea of what we're doing. So I'm just going to leave it running and see. Let's just take some notes and comments as this happens. So one thing we can notice pretty early on, we're kind of noticing this gradient of 0 is here, and we have a layer of 1s, a layer of 2s, we're going to have a layer of 3s, and then it keeps going. We have a layer of 4s, and then this should create a layer of 5s, 6s, and 7 should be the cost to get here. We can check that manually. Of course, we can go like 1, 2, 3, 4, 5, 6, 7. That's one of the shortest routes. We could also do it from the top, or we could even do it from here. 1, 2, 3, 4, 5, 6, 7. So Dijkstra is known as a greedy algorithm, meaning that in the priority queue, we always take the lowest value. This allows us to have this sort of gradient that always gets us the shortest path to every other node, starting from our start node. So that's really all there is to Dijkstra. Is not too hard once you can wrap your head around it. And let's go ahead and actually implement it. So we're back into the Replit where in our last section, we did the randomized DFS. Well, now we can head into the pathfinding file. And as you can see here, we have A star, which we're going to do right after Dijkstra. And we can actually just start with Dijkstra. We have 2 inputs. It's going to be the start node and the goal of want to reach. So let's go ahead and start with our implementation. If we follow the pseudocode that we just went through, we realize we need a couple of things. We're still missing some things. For instance, even though we know that this value is 7, how do we know what the path is? So to do that, we're going to create a couple of variables. We're going to create a parents map. And this is a hash map in JavaScript. We're going to create an explored map. This is going to help us tell our maze, sort of our maze thing, what tiles we've explored so far. And this is going to help us find the path when we find the shortest path. Let's create a priority queue. As you can see, we already have a priority queue imported from here over in utils. I really recommend that you read through this and see if you've never seen a priority queue. It's not overly complicated and it's super useful. So let's create a new priority queue. The way that we create it is we're gonna create a new variable called pq. We're going to use this import that we have up here. So let's create a new one. And this actually takes a function. Now I'm gonna do kind of a fancy JavaScript function. If you're not familiar with JavaScript, this is the syntax for it. Semicolon. What this means is I'm going to make an anonymous function. It doesn't have a name. It just takes 2 inputs, A and B. And then the function code should be in here. So I'm pretty much telling it how I want it to prioritize the items that I put in. So it's going to compare A and B. And I want to say, take A's cost, which in the cells that we already have prepared for you is going to be .f. F stands for the total cost for this function, for this cell. And we're going to return A.f is less than B.f. So this will create a sort of a comparison function. So whenever we send the cell in there, it'll compare it to the other ones using this function. Okay, so our first step is going to be to push the start node, this start cell, I mean. We're going to put the start cell in the in the priority queue, and we're going to set its f value, its cost, to 0. Remember, we can safely say that the cost of going from the start node to the start node is 0. So now this is really the entire starting section. We can get into the meat of the code, which is the while loop. In here, we can say while eq is empty equals false. So while the queue is not empty, and we can simplify this to a nicer exclamation mark saying while not this. Okay, so while the queue isn't empty, oh, and remember parentheses here, I forgot to mention. We're going to pop from the queue. Let's create a new variable called current, and it's going to receive whatever we pop from our priority queue. And then as soon as we do that, I want to go into the explored path array, and I want to push this cell because I want the explored path to contain every cell that we have discovered so far. And the way that we discover them is by popping from the queue. So the first thing I want to check, well, is current equal to our goal? If it is, then, I mean, there's not much else for us to do. We found it. I'll complete this function at the end because there's one step that we still need to do. So let's just go through and see what happens if this isn't the goal. Well, first, let's mark it as visited. Whenever we pop from the queue, we want to make sure that we mark the cell as visited. And then we want to basically travel through all its neighbors and see what weights we can, what paths, what new paths we can find. So the way that we're going to do that is we're going to do a for loop, and we're going to say let neighbor of current dot, and then we're going to use a helper function that we already have created for us called get non blocked neighbors. So this way we're going to get any neighbors that don't have a wall between our cell and the neighboring cell. The first thing we're going to check is if this neighbor cell is already visited. I just like to continue. I don't need to redo this. This might just end up being an infinite loop if I don't skip the cells that we've already visited. And here we're gonna do the part of the code where we have this alt thing. I'm gonna call it alt cost. This alt cost is gonna take whatever the cost was for this original cell plus 1. I know that this is the cost of going from my current cell to any neighboring cell because that's just what we've set it to. It costs 1 to, if we go over here, it costs 1 to move from one cell to another. So here we're going to check if the neighbor's cost is equal to infinity. And by the way, I did forget to mention, but in the background, all of these cells that you're receiving, they have a default of infinity for their cost. So that's why we didn't do it here in the beginning because it's already done for us. So let's go ahead and say if it equals infinity, or if this new cost that I found is better than the cost that my neighbor currently has, that means I found a new way to get here that's actually cheaper. That's also why it's called a greedy algorithm, because it's kind of looking for the cheapest options at every time that we can use to get to a specific node. So after figuring out a new cost, we're going to push this neighbor into the queue, the priority queue, because we want to reanalyze it and see if there's anything else that we can, any more profit or better costs that we can get from it. Then we're gonna go to this parent hash map. We haven't done anything with it yet, but we're actually going to one quick thing, I had a typo here. This is an explored map. It's explored path. So this parents map is basically going to set current, apologies, no, it's going to set neighbor to current. If you're familiar with hash maps or dictionaries in Python, it's basically the same thing. We're creating a link between this neighbor to current, which is its parent. So this way we can run through the parents array, the parents map, and find the optimal path that our algorithm found. So this right here, if we find our goal, should return something that we'll implement in a second. If we don't find our goal, this while loop will finish and we'll get into this return statement. This will never happen in our maze, but in case it does, let's just send the explored path and send an empty array. This explored path is the first output of this function, and then the second output is the final path. So what's the path from the goal that we want to the start, the very start. And that's what we're actually going to do here. We are going to create a final path variable. And we're going to do that using a function called construct final path. We're going to pass it the parents and the goal. So it's going to start from the goal and go into the parents array and just backtrack basically its way, creating a final path. And then we will return explored path and final path. Now we actually have the fun job of implementing this function. So let's go ahead and do that. We're going to create this function. We don't need to export it like the other ones. We can just create it. It takes a parent array and it takes a specific cell. And we basically want to find the path that it took to get this cell. So let's create a new variable called final path. And let's say while cell. So while cell is not null where this cell variable exists, let's push into the final path the cell, and then let's set the cell equal to parents to the value that's stored for it. So as you can see here, we store a value for every cell, which is its parent. And at one point we'll get null because it means it reached the end of the path. Now there's one little thing that we need to do before we can return this final path we constructed. As you can see, I am pushing to it the cell, which would be the goal, and then its parent, and then its parent, and its parent. So this path is actually reversed. It's going from the goal all the way back to the start. So let's just reverse it. So it goes from the start to the goal. Okay, so this should be the entire algorithm, and we can actually go ahead and test it out in the maze generation. Let's make sure we reload the page. Let's generate a maze. And let's see if we can pathfind Dijkstra. There we go. So you can see it go ahead and how it starts exploring and then finds the goal. Over here, we have some stats. It says it explored 137 cells and the final path was 48 cells long. If we clear the board and let's try to get some distance between these, we can see what we went through in the slides. It does this sort of diagonal shape and it finds the best path to that goal. All right, so that's it for Dijkstra's. And let's go back to the slides. We can actually jump right into A star. So A star, let me begin here. Okay. So A star is actually super common. And when I say super common, I mean it's in a way it's used in almost every navigational app, Google Maps. It's used in lots and lots of video games for pathfinding. It's super useful, and we'll see why when we finish coding it up, or when we go through this actually. Let's start going through A star. A star is based on Dijkstra's, and it actually takes very little change to make Dijkstra's into A star. But let's go through and see what the difference is. Well, the very main thing is in A star, there's a very important concept. F equals G plus H. Every cell has an F cost, which is the total cost to get to that cell. And then G is the cost to get to that cell from the start. And H is called a heuristic. Well, let's just talk about what is a heuristic. Uh, gee, let me quickly get rid of this. I accidentally left that in there. Okay, let's talk about what is a heuristic. Well, a heuristic is basically just a calculated guess. The way that we use a heuristic to our advantage is, let's take this example. It's very similar to our initial one, except we moved around the start and the end goal. So we have f equals g plus h. G is the distance from a certain node to our start node. We already know that using Dijkstra's though. So say that we move up here to this node at the very edge of the maze. We know that the distance from start to here is 1. So we can just put a 1 here for now. We already know how to calculate this. But how do we calculate the h? Well, if a heuristic is just a calculated guess, let's see what happens if we plug in the, let's say from this node, the distance to get to the end node. One way we can do that is by taking the Manhattan distance, which is quite literally just basically just going and finding the distance. It can be rise over run, or it can be anything similar. For instance, the Euclidean distance turns this into a triangle and uses the hypotenuse. In our case, let's just use the Manhattan distance for a bit of simplicity. So let's see, if we move 1, 2, 3, 4, 5, 6, 7, the heuristic would be 7. 7 plus 1 equals 8. So let's plug 8 into this cell. And let's say that we add it to our priority queue. That's why we made it yellow. As you can see, this heuristic doesn't actually care if there's a wall in between. It doesn't even know there's a wall. We're not really going through these nodes. We're just calculating the distance. That's why we call it a guess, because we're not really sure. So let's see what happens if we do that for a couple of examples. If we do it for this node, we realize we get a 6. Why? Because there's a 1 distance to here, and then there's 1, 2, 3, 4, 5. That means this is a 6. Let's do it for down here. This is also a 6. If you think about it, when we put these in a priority queue, this is where we're actually taking advantage of the priority queue. It's going to pop these 6s before this 8. Therefore, A star sort of prioritizes a direct path to the end node rather than just trying to layer by layer as a gradient trying to get all of them. So let's see what happens if we do this 6. Well, this turns into an 8. Let's see, 1, 2, 3, 4, 5, 6. And then 1, 2, 6 plus 2 is 8. So in a way, we want to keep this stable balance of, if we move this way, we are 1 step less further away from the edge, from the end goal, and 1 step further from the start goal. So these should all be 6 in reality. So let's just go ahead and fill all of these out. And as you can see, we create this sort of stable path all the way to the edge, a direct path. And these 8s are never even visited. We don't need to. We already visited using this heuristic, the smaller values. This 8 isn't even actually ever touched at all. So this is basically what the heuristic does, and it's what makes A star so powerful. If you know where the end goal is, you can use a heuristic to accurately just go towards it. So let's go ahead and code it up. It should actually not take a lot of time because we're gonna go ahead and just copy everything that we have inside of Dijkstra. And let's just make some simple changes. So let's see what changes we're gonna need to make. Let's just slowly go through this the same way. So we still need a parents map. We still need an explored path. We still need a priority queue. And it's going to do the same thing. It's going to calculate the Fs, which take the total value. The difference starts here. Our start node has a total cost of 0, but it also has a total distance of 0 to itself. Remember that F equals G plus H. Now, we don't actually need to calculate the H for the start node. So let's continue and see what comes next. We still need our priority queue. We still need to make sure that we pop things from our priority queue. We explore the path. When we find the current being the same as the goal, we still need to construct the final path. So we'll use the same function. And we still need to return. Then we still need to mark it as visited. Everything is actually really similar. This is all the same. And here's the main difference, where we calculate the alternate cost. The way that we're going to do it is, instead of taking the F value of our previous node, we're going to take the G value. We're going to say this alternate cost is equal to how long it took me to get here plus 1. And then what we're going to do is we're going to check if this alternate cost is less than my neighbor's G cost, which by default will be set to either infinity or 0. It will be set to infinity. We can actually do this way. I know we did it differently up here. It doesn't matter because JavaScript understands that 0 or any integer is less than infinity. So let's just keep it this way for simplicity. Now, let's replace this line right here. We're going to need to calculate the neighbor's G value. The G value will be the alternate cost that we already calculated. Now we need to calculate the heuristic. Well, we need to make a heuristic function that can do this for us. And that takes the neighbor and the goal. Let's go ahead and do that. Right before, let's finish this function here. And really simply, as we had before, .f is quite literally just G plus H. So let's make this heuristic function. Make a new function called heuristic. It takes A and B, to say it takes 2 cells. And it will return the Manhattan distance in this case. And we can do this in a one-liner by saying, give me the absolute value of A's row minus B's row plus the absolute value, so the distance pretty much, of A's column minus B's column. All right, so this is all that we needed to change. The very simple changes were just changing how we calculate the cost and creating a heuristics function. So let's see if it works. Let's jump over to our site. Let's see if we can reload the page. Let's generate a maze first. Okay, and then let's try to path. Let's actually move the start and goal. Let's get them a little further apart. Okay, and path find with a star. So let's just take a quick look at the stats and see what the difference could be. With a star, we explored 371 cells. With Dijkstra's, we explored 373 cells, so 2 more. In general, a star will always be faster or explore less cells, I mean, simply because of this. We can see here that Dijkstra does this diagonal pattern. But if we do A star, we can see it just shoots directly towards the end goal when there are no obstacles. So yep, that's gonna be it for the practical applications of this event. Thank you.
Great.